Hello and welcome. In this video, we're going to explore three totally different situations where the derivative arises: motion, geometry, and density. The first one, motion, is something that we've talked about in a previous packet, back in packet 4. You might recall that we had a robot, or generally a particle, moving along a number line. And we graphed the position function as well as the velocity function. This was, again, back in packet 4. So here we're going to transition from the visualization of the graphs of those functions to their algebraic representations. And we're going to add a third concept, acceleration, which is the rate at which velocity is changing. So let's review all three concepts. We have the position function that's represented by s of t. And as a physics detail, you can think of the position as the displacement relative to 0. So the displacement relative to the 0 position. But if that doesn't make sense, don't worry. Just think about the position as some number along the number line. So in our picture, the example is the position is at negative 2. The position of this dot is at negative 2. Now velocity, v of t, is the rate at which the position function changes. Using our new derivative concept, we can write that velocity is the derivative of the position function. In other words, s prime of t. And that's what we have right here. So velocity is s prime of t. And then acceleration is the rate at which the velocity function changes with respect to time. So it's the derivative of the velocity function. So we can write it as v prime of t. Acceleration is something that is constant, at least on the Earth, on the crust of the Earth. It's a constant 9.8 meters per second squared, just to give an example. But it depends on where you are. I mean, that's just the acceleration due to gravity. There are many other things that, many other accelerations that cause objects to move or to change their velocity. To get the acceleration, you can either take the derivative of the velocity function, or you can start with the position function, take a derivative, then take another derivative, a second derivative, and you'll arrive at the acceleration function. So we can either write it as the first derivative of the velocity or the second derivative of the position function. So s double prime of t. Note that velocity can be positive or negative. Positive means movement to the right, negative means movement to the left. But when we're talking about the speed of the particle, which doesn't have a sense of direction, if you're going 60 miles per hour, that doesn't say where you're going, just says that you're going, how fast you're going. The speed of the particle will always be positive. And what we can do here to get the speed from velocity, at least in our setup, is take the absolute value of the velocity function. That'll give us the speed of the particle. So there you see those absolute value bars around the velocity. So as an example, if velocity is negative 3 meters per second squared, so that would be moving to the left 3 meters per second squared, speed would just be 3 meters per second. Whoops, sorry. Let me back up. If velocity is negative 3 meters per second, those are the units for velocity, then speed would just be 3 meters per second, period. Okay, well, let's take a look at example 1. It says that the position of a particle is given by the equation s of t equals t cubed minus 6t squared plus 9t, where t, which is here greater than or equal to 0, is measured in seconds and s is measured in meters. Again, s, the position can be positive and it can be negative, just like velocity and acceleration, as a matter of fact. So the first question is find the velocity at time t. And to get that, we'll just take the derivative of the position function. So we have velocity is the derivative of the position function. Using our new derivative shortcuts, we can write 3t squared minus 12t plus 9. So remember, the power rule says the 3 multiplies in front. You subtract 1 from the exponent to get a new exponent of 2. Do the same thing for the minus 6t squared. Multiply that 2 in front and subtract 1 from the exponent. That's what the power rule says. And then for the 9t, we can think of that as a line whose slope is 9. So you can think about it visually for that derivative. So there's the velocity function as a function of t. Then it says, what is the velocity after 2 seconds? Well, that's just going to be v of 2. We'll take 2. Oops. We'll take 2. Take 2. No. We'll take 2 and plug it into the velocity function. And in this case, you get -3 meters per second. Yeah, just like in the example. That was a total coincidence. Next, we're asked, when is the particle at rest? Well, this is like asking, when is velocity equal to 0? So I'm just going to write, when is velocity equal to 0? That's basically what this question is asking. Well, we have the velocity function at any time t, so we can set that equal to 0. And what I'm going to do is just divide both sides by 3, because I see that common factor of 3 in all of the terms. Then go over to here, factor the left-hand side. 3. And then set each factor to 0, and we get t equals 1 and t equals 3. Remember that we have units here, so we're going to write for the time values, they're in units of seconds. And those are the 2 times when the particle is at rest, when t equals 1 second and when t equals 3 seconds. That's where velocity is 0, so the particle's at rest. The next question asks, when is the particle moving in the positive direction? So this is equivalent to asking, when is v of t positive, or greater than 0 is another way of writing positive. That brings you down into a mathematical context where you can then solve things. Well, let's write what v of t is. It's 3t squared minus 12t plus 9. And then we'll write, that's what we need to be greater than 0. And just like we did a moment ago, to solve this, we're going to need to factor the polynomial. Now here, we can divide both sides by 3, or I'm just going to write an alternative way of doing it, which is factor out the 3. So you get t squared minus 4t. That's 4t, not 40. Very confusing. And then 3 times t minus 1 times t minus 3. So factor it all the way. Now what we do is a technique that back in pre-calculus you learn how to do, which is solve an inequality like this. Actually, you might have learned it even earlier than that, but this is a good time to review it. What we need to do to figure out when this expression is positive is first figure out the t values where the expression might change signs. And those will be the same t values that we were just looking at a moment ago, t equals 1 and t equals 3. Because at those t values, velocity will be 0, and 0 is right on the boundary between positive and negative numbers. So when t equals 1, velocity is 0, and so velocity might be changing from negative to positive, or possibly positive to negative. So those are going to be the key t values, again, that we're going to look at. And we're going to put those t values on a number line. This is the t number line, not the position number line, just to be clear. And we're going to write t equals 1 here and t equals 3 here. Just for reference, I'm going to put 0. And notice I'm not writing anything to scale. So the distance between 0 and 1 and 3 is totally off balance. But that's okay. All we're trying to do for this graph is to extract out the places where velocity is positive. So this is just a step along the way. It's not the final goal, so I don't have to make it perfectly to scale. Now what I'm going to do is make a row here for the velocity values. So this row is going to represent all of the values of v of t. Whether or not the values are 0 or positive or negative, that's what we're going to capture right here. And this is something that is going to carry on to future packets. We're going to use the same kind of technique, the same sign analysis, as we're going to call it, in future packets. So it's worth paying attention to here. Now we already know that velocity is 0 at t equals 1 and t equals 3. So we can write that's the value of velocity at those t values. And then to figure out what the sign of the velocity function is on the intervals in between, we can just take a little number, like maybe 0, for example, plug it into t, and plug it into v of t to figure out if v of t, the velocity, is positive or negative there. Let me do that scratch work off to the side. I'll go ahead and use a color like that. I really need to work on my color practice, you can tell. So here I'm going to do some scratch work off to this side. I'm going to write when t equals 0, v of 0 is, and I could go back to the original velocity function and plug these in, but what I'm going to do is make use of the fact that I have the velocity function factored here, and all I want to know is what the sign of velocity is. So all I need to know is whether or not these factors are positive or negative. So see here I have 3 times -1 times -3. But here what I can think is I have a positive number times a negative number times a negative number, which is positive overall. So this is just a shorthand notation for this, and I wanted to show you why I'm using this shorthand notation and what it looks like if you see it in the future. But basically what we've done here is just shown that velocity at t equals 0 is positive. So what I'm going to write over here is that at t equals 0, the velocity is positive. Now it's going to stay positive on the interval from 0 to 1 because we marked down the only t values where velocity might change signs. So it's not going to change signs when t is less than 1. It's just going to be positive that whole time. Now when t is between 1 and 2 and 3, so for example t equals 2, well there we might have a different sign. So let me do t equals 2. Now here I'm going to go ahead and just write down the signs. So we have that factor of 3, which is positive. And when t equals 2, we can think 2 minus 1 is 1, which is positive. Then when t equals 2, 2 minus 3 is -1, which is negative. So when I plug in t equals 2 into the velocity function, I get a positive times a negative, which is negative overall. Right? An odd number of negative factors gives you a negative number. An even number of negative factors gives you a positive number. So on that whole interval from 1 to 3, we're going to get negative for velocity. Now we can do the same thing, plug in t equals 4. So t equals 4. And we're going to get positive for all 3 of those factors. Notice that the t equals the 3 factor never changes signs. It's always positive, so that's always positive there. So it really boils down to what the t minus 1 and t minus 3 signs are. And here, when t equals 4, those are both positive. So overall, we get a positive velocity on that entire interval. All right, so now we know exactly where velocity is positive. It's positive right here when t goes from 0 to 1, and it's positive over here when t is bigger than 3. So putting that all together, we can write when t is between 0 and 1, and when t is greater than 3, we've got solutions. Now technically there are units, but they're sometimes a little bit annoying to write in here, so I'll forgive you if you don't write units here, but definitely when you can, when you just have a number, just write those units in there. There's seconds for time. Alright, so moving along. How are we doing on time here? Alright, moving along. The next part says to sketch the diagram to represent the motion of the particle. And here's what this means. It means we're going to draw a position number line. So I'm going to label that number line S. And we're going to show what the path of the particle is above this number line. So if you just drew a picture or a graph where you only had that number line, then you'd be scribbling on that number line to show the motion of the particle, and it'd be hard to tell which direction it's moving. So we're going to rise above the number line just so we can show the direction that the particle is moving as time is passing. So it'll show the position over time. Now there are 3 t values in this problem that are going to be important. Those are going to be t equals 0, t equals 1, and t equals 3. Those are important because t equals 0 is the starting time. Remember, at the very beginning we were told t is greater than or equal to 0. T equals 1 and t equals 3 are times when the velocity might be changing. And in fact, from our previous part, we know that the sign of the velocity is changing. So, the particle is moving in the positive direction, and then at t equals 1, it changes and moves to the negative direction. Then when t is equal to 3, it turns around and moves in the positive direction after that. So those are key t values where the particle is going to be changing directions. So let's find the position of the particle at those 3 t values. Well, at t equals 0, we can find the position by plugging 0 into the position function. And for this one, you want to go back to the position functions. That's t cubed minus 6t squared plus 9t. So for this first one, I'm going to write that all out. So this is going to be 0 cubed minus 6 times 0 squared plus 9 times 0, and you just get 0. Now s of 1 is going to be, it turns out, 4, and then s of 3, it turns out, will be 0. Again, plugging those t values into the position function to get the position. So let's go ahead and label those positions on the position function, or on the position number line. Those are key turning around points. Now we're going to write the position when t equals 0. The position is 0, so we're going to illustrate that by putting a dot right there. And we'll just label it t equals 0. Then the particle moves in the positive position direction because velocity is positive. When t goes from 0 to 1, velocity is positive. And so the particle is going to move from a position of 0 to a position of 4 over that time interval from t equals 0 to t equals 1. So we'll put the dot right here that represents the position of the particle at t equals 1. And I'm going to draw the motion there like this. So t equals 0 to t equals 1 looks something like this. And I'll draw arrows to represent that the particle is moving to the right over that time interval. Now at t equals 3, the position is back to 0. So at t equals 3, the position is 0. And on the interval from t equals 1 to t equals 3, velocity is negative. That means we're moving to the left. So from t equals 1 to t equals 3, we're moving from a position of 4 to the left towards a position of 0. Let's draw that. Again, I'll write arrows down to represent the movement to the left. Then after t equals 3, velocity is positive again, which means we're moving to the right. So we can continue the path, the epic journey of the particle as it goes to infinity and beyond. So that's the complete picture of what the motion of the particle looks like over time. Now again, the particle's not really moving up, it's just staying on this position number line. But in order to represent this motion of the particle, we rose a little bit above that number line, because otherwise it would just look like a big giant line on the number line, a shaded part of the number line. That's not going to really tell us all that much. All right. Now the next question asks, find the total distance traveled during the first 5 seconds. And here we're going to make use of those t values where the particle turned around. So we're going to look at, for example, the interval from t equals 0 to t equals 1. We're going to look at that distance that was traveled. Now, if we drew a picture, then we can see from the picture exactly how far the particle traveled. It traveled a distance of 4, because it went from a position of 0 to a position of 4 over that time interval. But if we didn't draw the graph and didn't have this picture to look at, what we could do to calculate that distance traveled over that first time interval would be something like this. We can write the absolute value of, let me switch over to blue, absolute value of the position at t equals 1 minus the position at t equals 0. It's like the final position minus the initial position, but with absolute values there just to make that, that change in position positive, so that we're talking about a positive distance as opposed to a displacement. So here the position at 1 was 4, the position at 0 was 0. So calculating this, we get 4, and I'll write the units here, which are in meters. On the next leg of the journey, from t equals 1 to t equals 3, we can calculate the distance traveled, again, by looking at the difference of in the position values, but with an absolute value bar there to ensure that we're talking about positive distances traveled instead of displacements. So here the position at t equals 3 is 0, the position at t equals 1 is 4. 0 minus 4 is negative 4, but then the absolute values make it positive 4 meters. Now we still have some time left because we're looking at the distance traveled during the first 5 seconds. So there's t equals 3 to t equals 5 still to count. And that means we're going to do this again. We'll do s of 5 minus s of 3. Now s of 5 you can figure out by plugging 5 back into the position function, and you should get 20. And then s of 3 was 0. So taking the difference and then the absolute value, you get 20 meters. So these are the distances on each leg of the journey. Then to get the total distance, we add them all up. 4 plus 4 plus 20, which is 28 meters. It's quite a long way for a particle to travel in 5 seconds. Okay, the next question asks, find the acceleration at time t and after 3 seconds. Remember, acceleration is the derivative of the velocity function, also the second derivative of the position function. But here we have the velocity function already, and I'll just scroll up so you can see what that was. Remember, we got the velocity function at the very beginning. It was 3t squared minus 12t plus 9. So if we take the derivative of that velocity function, we'll get 6t minus 12. 6t minus 12. That's 6t minus 12. All right, then we can take 3, and that's one of the things we were looking for. So then we can take 3 and plug it in to the acceleration function that we just got, and we get 6. And the units here for acceleration will be in meters per second squared. It's going to be units of the position function per units of time squared. Okay. Now the last question here asks for when is the particle speeding up and when is the particle slowing down. And to demonstrate speeding up and slowing down, what kind of scenarios you'd be looking at there, I'm going to enlist the help of my friend the water droplet. So this water droplet is going to represent the particle moving along the number line. So if you're talking about speeding up, there are two situations where the particle or the water droplet can be speeding up. One is if the velocity is positive, and so what I'll do is point water droplet, Mr. Water Droplet, in the positive direction, and have him move in the positive direction. So here velocity is positive. Now if acceleration is also positive, so in the same direction as the velocity, it's going to push the water droplet to go faster. So again, if velocity is positive and acceleration is positive, that acceleration is going to cause velocity to go faster in that positive direction. So that would be one case where you'd be speeding up. Another case where you could be speeding up is if the water droplet here is moving in the negative direction and acceleration is negative. That's going to again push the droplet to move faster in the negative direction. So in summary, the droplet or the particle in general is going to be speeding up when the velocity and acceleration have the same sign, either both positive or both negative. And the particle will be slowing down if the opposite happens. If, say, velocity is positive and acceleration is negative, well, now that acceleration is going to slow the water droplet down. If it continues, the water droplet will finally stop, turn around, and then be accelerated, speeding up in the negative direction. But at first, if the water droplet is moving in the positive direction and its acceleration is in the negative direction, the acceleration will slow that water droplet down. Or if the water droplet's moving in the negative direction, so velocity is negative and acceleration is positive, that's going to slow the water droplet down as well. So let's summarize those two ideas. The particle will speed up if velocity is positive and acceleration is positive, or if velocity is negative and acceleration is negative. In other words, same sign. And it will slow down if velocity is positive and acceleration is negative, or velocity is negative and acceleration is positive. In other words, opposite signs. Okay. Just for reference, I'm going to write down acceleration here in a factored version. So we can factor out the 6 from acceleration. It was 6t minus 12, so factor out a 6, and we have t minus 2. And I'm going to write down the t value where acceleration might change signs. That's t equals 2. That's where acceleration is equal to 0, which is, again, is right on the boundary between positive and negative numbers. Now what we're going to do is try to catalog the signs of velocity and acceleration. So put everything together in one big picture. So I'll draw a number line. This is going to be the t number line, starting at t equals 0. And I'll collect all of the t values where either velocity or acceleration might be changing signs. And again, these are the t values where velocity and acceleration are 0. Then we're going to make a row for velocity, just like we did before. A row for acceleration, just like we did before. No, not like we did before. What am I talking about? This is a long video. And we're going to write down the places where velocity was 0. That was t equals 1 and t equals 3. And then in the acceleration row, we're going to write where acceleration was 0, and that's at t equals 2. That's where acceleration is 0. And now we're going to write the signs of velocity and acceleration on each of these intervals. Now we already did velocity before. Once again, we said velocity was positive here on the interval from 0 to 1, and it was also positive at 0 as well. And negative on the interval from 1 to 3. So it was negative on the interval from 1 to 2, negative at 2, negative from 2 to 3. I'm going to write a negative on each of those in each of those places, and it's kind of hard to see why right now, but just to be consistent with some future packets, I'm going to write it in this way. And then here, after t equals 3, velocity was positive. So again, we're just copying down what we had gotten in a previous part. Now for acceleration, we have to figure it out. We have to plug in some t value that's less than 2, figure out if acceleration is positive or negative there, and then some t value that's greater than 2, and figure out if acceleration is positive or negative there. I'll do that down here. So a of, let's say, 1, that's going to be a positive 6 times a negative number, and negative 1 minus 2 is going to give you a negative number, which is negative. And so acceleration is negative here, and it's going to be negative on the interval from 0 to 1 and from 1 to 2 as well. Then we'll check a of, let's say, 3. Just pick any t value that's greater than 2. 3 is a nice one. And we're going to get positive, because 6 is always positive, and then a positive number when we plug 3 into the t minus 2 factor. 3 minus 2, that's positive. So positive times a positive is positive. And so at t equals 3, acceleration is positive, and that includes also then the intervals from 2 to 3 and from 3 to infinity. Because again, acceleration is only going to change signs possibly when t equals 2. So now we've got a graph that, or a table here, that shows the sign of velocity and acceleration on each time interval. For example, from t equals 0 to t equals 1, velocity is positive and acceleration is negative. So since they have opposite signs on that interval, we can say that the particle is slowing down. Again, that's movement in the velocity is positive, but acceleration is negative, so that's going to slow the particle down. They're fighting against each other. Then from the interval t equals 1 to t equals 2, velocity is negative and acceleration is negative. So there, the particle will speed up. If velocity is negative and acceleration is negative, it's going to push velocity even more in the negative direction. So that would be speeding up. Then from t equals 2 to t equals 3, velocity and acceleration have opposite signs, so they're fighting against each other, and that's going to slow the particle down. And then t is greater than 3, velocity is positive and acceleration is positive, so same signs, that'll make the particle speed up. Let's write down all of that here. Speed up, slow down. So it's, again, speeding up when there's the same sign, that's t equals 1 to t equals 2. And t is greater than 3. And then slowing down when they have opposite signs, that's t is between 0 and 1. Oops. And t is between 2 and 3. Okay, so there we have it. Thanks for watching, and Water droplet says bye. See you in the next part.